Hi students, welcome to the fifth lecture of Basic Mechanical Engineering. And in the previous lecture, we have studied about the basics of thermodynamics and the ratio of specific heats and some thermodynamic processes. We already discussed about the thermodynamic process like a constant pressure process, constant volume, constant temperature, adiabatic process, etc. And we have derived the work and heat transfer equations on this process. So in this lecture, we are going to discuss more about some thermodynamic cycles that are commonly used in engineering practices. Okay. So what are cycles? What are thermodynamic cycles? I already discussed in the lecture 3 that when a system in a given initial state experiences a series of processes and returns to its initial state, the system is said to be undergone a cycle. That means at the end of the cycle, all the properties of the system have the same value they had at the beginning. Okay, so thermodynamic cycles is mainly used in many applications like car engines, refrigerator, etc. And we are going to discuss more details about that in the upcoming lectures. So mainly thermodynamic cycles are classified or main thermodynamic cycles used today are Carnot cycles, Otto cycle, and diesel cycle. So these three thermodynamic cycles are known as reversible thermodynamic cycles, and because of that, these are ideal cycles. And what is reversible cycle? I already said that a reversible process is a process in which both the system and the surroundings return to its original position when the direction of that process is reversed, or when the direction of that process is reversed, both the system and the surroundings come back to its original state. So that type of process are known as reversible process, and the reversible process in which entropy of the system remains zero, or there is no entropy change of the system remains zero, or there is no change in the entropy of the system. Actually, all the thermodynamic cycles or thermodynamic process are non-reversible, and hence we cannot achieve these reversible cycles. And because of that, we call these cycles as ideal cycles. Okay. So why we are interested in reversible cycles? Because the reversible cycles are the more efficient cycles. Also, reversible cycles cannot be achieved in practice because of the irreversibility associated with each process. And when a process is acting or process is happening, there are so many irreversibilities due to heat transfer, work transfer, etc. And those cannot be eliminated completely. Because of that, reversible cycles are ideal cycles and cannot be created or achieved in nature. Also, reversible cycles also serve as a starting point in the development of actual cycles, and which are modified as needed to meet certain requirements. Because reversible cycle is considered to be the starting point of all the cycles. That means when we want to make thermodynamic cycles, we always thinking about the reversible cycles, and from that we are developing the actual cycle. So that is why reversible cycles are always important in thermodynamic practices. Okay. So we go into the first reversible cycles, which is known as Carnot cycle. This cycle is proposed by Sadi Carnot in 1824, and it is an ideal or imaginary cycles, and also it is a reversible cycles. This Carnot cycle consists of four processes. There are two isothermal processes, two adiabatic processes. The Carnot cycle consists of four processes, and in this heat is supplied and rejected isothermally, and expansion and compression of air takes place adiabatically. In a Carnot cycle, in an ideal Carnot cycle, air is the working fluid, and heat is supplied and rejected into the air isothermally or constant temperature, and air expand and compress adiabatically. Adiabatical process means without any heat addition or rejection. Okay, and also reversible adiabatic process are known as isentropic process because entropy of the system remains constant in this process. So let us check into more details of this process. I already said that there are 4 processes: 2 isothermal process and 2 adiabatic process. Here it is shown in the figure, and this is the pressure volume diagram of this Carnot cycle and temperature entropy diagram of this Carnot cycle. And the 2 isothermal and adiabatic process are shown in the figure. Okay, we will go to more details about this. So in process 1 to 2, we have a piston contain some gas at some temperature TH, and the temperature of the system TH will be constant, and there is an energy source which is at a temperature TH. Because both the system and the surrounding or the energy source have the same temperature, heat cannot flow into the system. Okay, when the starting of the reversible adiabatic expansion process, the initial temperature of the gas is TH and the cylinder head is in close contact with the source temperature TH. Okay, and at this moment heat cannot flow into the system. Okay, next the gas is allowed to expand. The gas inside the cylinder is allowed to expand freely because of the temperature. What happened? The gas in the cylinder expand freely, and because of this self-expansion, the piston is moving from this position 1 to 2 slowly. Piston is moving from position 1 to 2 slowly. Okay, and because of this expansion process, the temperature of the gas tend to decrease. Okay, temperature of the gas tend to decrease, and when a small change in the temperature occurs, or when the temperature drops by an infinitesimal amount dt, or the temperature inside this chamber, temperature of this gas inside this chamber changes and drops by an infinitesimally small amount dt, some heat is transferred from the reservoir or energy source to the cylinder. Okay, some heat is transferred from the reservoir into the gas or inside the cylinder. Okay, and then raising the temperature to TH. അതായത് ചെറിയൊരു ടെമ്പറേച്ചർ ഡ്രോപ്പ് ഇവിടെ ഉണ്ടാകുന്നത് കൊണ്ട്, ഈ ഒരു ഫ്രീ എക്സ്പാൻഷൻ കൊണ്ട് ചെറിയൊരു ടെമ്പറേച്ചർ ഡിഫറൻസ് ഇവിടെ ഉണ്ടാകുമ്പോൾ, ഡി ടി എന്ന് പറയുന്ന ഒരു ടെമ്പറേച്ചർ ഡിഫറൻസ് ഇവിടെ ഉണ്ടാകുമ്പോൾ എന്ത് സംഭവിക്കും? എനർജി സോഴ്സ് നിന്ന് ഒരു ചെറിയ എമൗണ്ട് നമ്മൾ ഈ ടി എച്ചിലേക്ക് ഒരു ഹീറ്റ് ആഡ് ആവും. ഓക്കെ, and when, since the temperature difference between the gas and the reservoir never exceeds a differential amount Tt, this is a reversible heat transfer process. എന്ന് വെച്ച് കഴിഞ്ഞാൽ ഇവിടെ ഡി ടി എന്നാണ് ചെറിയൊരു ടെമ്പറേച്ചർ ചേഞ്ച് ഉണ്ടാകുമ്പോൾ തന്നെ എനർജി സോഴ്സ് നിന്ന് ക്യു എച്ച് എന്നുള്ളൊരു ഹീറ്റ് നമ്മുടെ ഗ്യാസിലേക്ക് ആഡ് ചെയ്യുന്നുണ്ട്. അതുകൊണ്ട് തന്നെ എപ്പോഴും ഈ ഒരു ചെറിയൊരു ഡിഫറൻസിൽ മാത്രമേ അത് ഡിഫറൻസ് മാത്രമേ ഉണ്ടാവാൻ സാധ്യതയുള്ളൂ. അതുകൊണ്ട് തന്നെ ടി എച്ച് എന്ന് പറയുന്നത് എപ്പോഴും കോൺസ്റ്റൻ്റ് ആയിരിക്കും. അതുപോലെ തന്നെ ഈ പ്രോസസ് എന്ന് പറയുന്നത് ദിസ് പ്രോസസ് is known to be a reversible process. Okay, so the temperature difference between the gas and the reservoir never exceeds a differential amount dt. This is a reversible heat transfer process. We can say that it is a reversible heat transfer process. Okay, so ഇവിടെ okay, so this process continues until this piston moves from position 1 to 2. Okay, when it reaches position 2, this process stops. Okay, It continues until the piston reaches position 2. The amount of total heat transferred to the gas during this process is QH. QH ആയിരിക്കും total amount of heat transferred to the gas during this process. Okay. നമുക്ക് ഇതിൻ്റെ PV ഡയഗ്രാം എങ്ങനെയാണ് ഉണ്ടാകുന്ന നോക്കാം. ഇവിടെ ഞാൻ കാണിച്ചു. Already said that this is the pressure volume diagram, and from state 1 to state 2, this is the graph of this constant temperature expansion process. Expansion ആയതുകൊണ്ട് തന്നെ the pressure will drop from P1 to P2, and the volume also changes from V1 to V2. And this is the temperature entropy graph, where temperature of the system remains constant during this process, that is TH. Okay. The process 2 to 3 is known as the reversible adiabatic expansion process. In this process, at the stage 2, the reservoir is removed and replaced by an insulation. That means the reservoir is removed and that cylinder is completely insulated, because of that there is no heat transfer into or out of the system. Okay. And the gas is continuing to expand and very slowly and doing work on the surroundings. That means the piston move from position 2 to 3. Okay. And because of that, temperature drops from TH to TL, because there is no heat addition takes place in this process, and it is a reversible adiabatic expansion process. Okay. And piston expand from 2 to 3, and during this process the temperature drops from TH to TL, and the movement of the piston is assumed to be frictionless, and the process is assumed to be quasi-equilibrium condition. That means it is a very slow process. Okay. Because of that, the process is reversible as well as adiabatic. Okay. And the pressure volume graph of this process is shown in this 2 to 3, shown as 2 to 3. This is the reversible adiabatic expansion process, and during process 2 to 3, the temperature drops from TH to TL. Temperature drops from TH to TL. Okay. And in the process 3 to 4, it is known as reversible isothermal compression process, in which that insulation is removed. The insulation at the cylinder head is removed, and the cylinder is brought into contact with the sink at temperature TL. Okay. Here that insulation, we are removing the insulation, and a heat sink is made in contact with this his cylinder. Because of that, okay. And when we are applying some force on the cylinder, and the work is done onto the system. Because of this force, the piston move from position 3 to 4. Okay. And it is known as compression process. That gas inside the cylinder is compressed with an external force, and because of that, the volume of the cylinder decreases and the pressure inside the cylinder increases. Okay. And because of this, the gas is compressed, its temperature tends to rise. Okay. The temperature tends to rise, and when the temperature rises an infinitesimally small amount dt, what happened? The heat is transferred from the system to the surroundings. Okay. Heat is transferred from the system to the surroundings. Okay. When a small temperature difference dt occurred in this system. Okay. And because of that, the temperature drop remains constant, and this system will be in temperature TL. Okay. So this process continues until this piston reaches from 3 to 4. When this piston reaches at 4, the process stops, and total amount of heat energy transferred from the system to the surrounding is QL. Okay, and the pressure volume graph is represented as curve 3 to 4 in PV diagram and a straight line because the temperature of the system remains constant. Okay, and temperature entropy diagram is shown in the figure. Okay, and the last process is the reversible adiabatic compression process. Process 4 to 1 or the last process in this cycle is the reversible adiabatic compression process. In this process, that heat sink is replaced by an insulator and and the low temperature reservoir is removed and the insulation is put back on the cylinder head. Because of that, heat transfer from the system or the heat transfer to the system will be zero, and it is said to be an adiabatic compression process. And the gas is compressed in a reversible manner from 4 to 1. The piston moves from 4 to 1 and the gas inside it is compressed. Because of this compression, the temperature rises from TL to TH. Okay, and the temperature rises from TL to TH during this reversible adiabatic compression process, and hence the complete cycle completes. And this shows the PV diagram is shown here, and process or graph 4 to 1 shows the reversible adiabatic compression process, and in TS diagram it is represented as a straight line because the temperature rises from TL to TH. Okay, or temperature changes from 4 to 1. Okay, so these are the four processes in a Carnot cycle, and now we are going to find out the work done of an Carnot cycle. So figure shows the pressure volume diagram of a Carnot cycle, and in this the area under the curve 1, 2, 3 gives the total work done by the gas during this expansion part of the cycle. Okay, and the area under the curve 3, 4, 1 shows the work done on the gas during the compression part of the cycle. 1, 2, 3 shows the area under the curve. 1, 2, 3 shows the work done by the gas, and area under the curve 3, 4, 1 shows the work done on the gas, and the total work done by this process is represented as the area under the complete curve 1, 2, 3, 4. Okay, this shaded portion is the total work done by the system. Okay, and the area enclosed by the path of the cycle 1, 2, 3, 4 is the difference between these two, and it is the net work done during the cycle. So now we need to calculate the efficiency of the cycle and net work done. We know that for an adiabatic process, isothermal process, heat supplied from 1 to 2, or the adiabatic process 1 to 2, heat supplied will be given as QH is equal to T into delta S, where delta S is the change in entropy of the system. Okay, which is equal to T1 into S2 minus S1, because in this process the temperature of the system remains constant, and that is T or T1, and the entropy changes from S2 to S1. Okay, so heat supplied during process 1 to 2 is equal to T1 into S2 minus S1. Similarly, heat rejected during 3 to 4, that is QL is equal to T into delta S, which is equal to T3 into S3 minus S4. Okay, entropy of the system at 3 minus entropy of the system at 4. Okay, so net work done is equal to Q input minus Q output, or net heat input minus net heat out, that is equal to QH minus QL. For an air standard cycle, there will be a higher temperature and a lower temperature, and heat flows from higher to lower temperature, and because of that a work is done by the system, and that work is equal to QH minus QL, and heat transferred from the higher thermal reservoir is QH, and heat transferred to the lower thermal reservoir is QL. So that efficiency of this air standard efficiency is equal to output by input. So output is the net work done by the system, okay, divided by input. Input is the heat transferred to the system, that is QH. So output is equal to net work done W divided by QH, and net work done is equal to QH minus QL and divided by QL, which is equal to 1 minus QL by QH. So this is the air standard efficiency or thermal efficiency of an air cycles or of an air cycle. So therefore efficiency of a Carnot cycle is eta Carnot is equal to 1 minus QL by QH, and we have already calculated QL and QH. Substitute the values of QL and QH here, which is equal to eta Carnot is equal to 1 minus T3 into S3 minus S4 divided by T1 into S2 minus S1. And from this temperature entropy graph, we can see that the entropy S3 and S2 remain same, or S3 equal to S2 and S1 equal to S4. Because of that, S3 minus S4 will be equal to S2 minus S1, and because of that eta Carnot is equal to 1 minus T3 into S3 minus S4 by T1 into S2 minus S4. These two terms cancels each other, and what we get is 1 minus T3 by T1, where T3 is the lower temperature and T1 is the higher temperature, that is equal to 1 minus TL by TH. Okay, so efficiency of a Carnot cycle is 1 minus TL by TH, or 1 minus lower temperature divided by higher temperature. Okay, so efficiency of a Carnot cycle depends only on the temperature at a lower temperature and higher temperature. Okay, so this is the equations of efficiency of a Carnot cycle. So we already said that a reversible cycle is not a practical cycle, and also a Carnot cycle is not a practical cycle. This is because in order to achieve this isothermal process in this system, in this Carnot cycle, the piston has to move very slowly, okay, so that the temperature remains constant during each heat exchange. Okay, I already said that when a temperature difference dT happened on the system, then immediately the heat is transferred from the system to the from the surroundings to the system. This is happened only when the piston moves very slowly, so that the temperature remains constant during heat exchange. But in order to achieve an adiabatic process, the piston has to move very fast, because adiabatic means there is no heat transfer occurred on the surroundings, and if the system moves slowly, heat transfer occurred on the surroundings, and in order to avoid that one, the piston has to move very fast, and that is, there is no heat exchange with the surroundings, since the isothermal and adiabatic process are taking place simultaneously. Because adiabatic happened immediately after isothermal process, and this slow and fast process cannot occur simultaneously. Because of that, the cycle is not practically possible. This is the reason why the cycle is not practically possible. So that is how a Carnot cycle works. For clear understanding of this process, I will show you an animated video. Just listen to it.
So now for the first process, process 1 to 2. This process is called isothermal expansion. Isothermal in thermodynamics means no change in temperature, or in other words, temperature is constant or not changing within this process. So what happens here is that the heat energy from the heat source is transferred into the ideal gas. As a result, the gas expands, which then increases the volume and decreasing the pressure. Now next, process 2 to 3, which is called an adiabatic expansion. Adiabatic in thermodynamics means that there is no heat transfer between surroundings and your system, or to put simply, all change in temperature is contained within a system, which as a result making the entropy zero. On this process, our volume increases and pressure decreases. Third process is the isothermal compression. So by compression, it means volume is decreased and as a result, pressure increases. On this process, heat energy from the gas is transferred into the heat sink. And finally, the last process. The last process is called the adiabatic compression. Since it's an adiabatic, all change in temperature is contained within a system, and our entropy is zero. Also, since this is compression, it means our volume decreases while our pressure increases. So that's it. That makes it a cycle.
So that's all for today's lesson, and we can discuss other topics in the upcoming lessons. Thank you.